All right, Chapter 10, Section 5. This is our second example from the Section 5 notes on using parallel and perpendicular lines. This is only a slightly more complex version of the first example, and also similar to the example in Section 4. In both of those cases, I started with the point and found the distance between that point and some given line. This one's only slightly different because now instead of a point and a line, now I have two lines. And so this may seem more complicated, but in fact, it just takes a really quick pre-step. Namely, on either of these two lines, it actually doesn't matter, but I can pick any point I want on either of the two lines and find the distance between that point and the other line. Whether I choose this point right here, that little y-intercept, and find the distance from that point perpendicularly to this other line, or I chose some other point infinitely further down here from its perpendicular distance from the other line, it's going to be the same distance everywhere. If it were a changing distance, that would mean that the lines intersect somewhere. And fundamentally, these lines are parallel. How do I know that? In the given example, I needed to find the distance between these two lines, but notice they have the same slope. The fact that they have the same slope means that these two lines are parallel. Why does that matter? These two lines will never intersect, which also fundamentally means that they're always the same distance apart from each other. And that matters because that means that on one of the lines, I can pick any point I want and find the distance to the other line, and it's going to be the same everywhere. So it actually does not matter which point I choose. Here's my suggestion. On either one of the lines, it doesn't matter which, pick the y-intercept. So I have two different y-intercepts to choose from here. Let's just choose that one. So moving forward, let's work with this y-intercept and figure out the distance from that y-intercept to this line. And that matters now because now this is exactly like the other two examples that we've done, the one previously in this section, as well as the one that we did in section 4, where now I'm just finding the distance between a point and a line. And so I'll use the same three-step process. So it may come in handy, say like, all right, I've chosen that y-intercept. Let me write down that coordinate point. Well, this one went left to right 0 and up 1. So my coordinate point here would be 0, 1. That's my coordinate point right there. And again, I could have chosen any coordinate point I wanted. The fact that I chose the y-intercept will make things a little bit more convenient, particularly for this process and for my second one, so on and so forth. So again, my suggestion, you can pick any point you want on either line, pick the y-intercept of one of the lines. Another kind of valuable step to do, now that I've chosen a y-intercept, I did this on this top line. The equation for that top line is this guy right here. There's that +1, that's the y-intercept, that's actually the exact point that I chose. So the fact that I chose it from this line, what might come in handy, just a little suggestion for you to do is cross it out now. Why? I cross out this equation because I've just reduced this equation down to 1 point. Okay, this is no longer an equation. This is the point 0, 1. It happens to be the y-intercept here by suggestion, but now I've taken this entire line, reduced it down to a single point. This is the other line that I'm going to compare that coordinate point 0, 1 to. These are the two things I'm going to find the distance between. Okay. All right. The reason I crossed it out is because if I went through the process of finding, if I happen to choose the wrong equation, then I'm going to find out where like the distance is between these two things. If I were to try to find the distance between this point and that line, considering the fact that it's on this given line, I would find the distance to be 0, which makes sense. It's on the line, but that would be a lot of work to just find that kind of obvious result. So by crossing out this equation, it reminds me that that's the line I'm finding the distance between. All right, so let's move on to the equation of this perpendicular line. Again, I need two things in order to find the equation of any line: slope and intercept. So in order to find slope, the first thing I'm actually going to want to do is I'm going to want to figure out the slope of my line. The given line that I have, I needed my perpendicular line to be perpendicular to this guy. And the way I can figure that out is by identifying the slope of this one. Well, the slope of this line is found right there, mx plus b, right? This 1/2 represents the slope of this line right here. And in order to find the perpendicular version of that slope, I'm going to be converting that slope into its perpendicular version using the negative reciprocal. So I would start with my given slope. This is the line that I'm going to connect it to, and I'm going to convert that using negative reciprocal. Flip the sign, flip the fraction. This is a positive 1/2, so it's going to become negative. The 1 over the 2 is now going to become 2 over 1. That's my perpendicular slope, which if I reduce that, that's just negative 2. So whatever else is true, the perpendicular slope that will connect these two lines, and more specifically that point to this line, has a slope of negative 2. Now, as a bit of a shortcut in this case, one thing I could do is I could just do a negative 2 slope from that point and create my line. But what we're going to need in this case, particularly for this example, is I'm going to need the equation of this line. So I have my slope. Now I need my y-intercept. But here's the convenient thing. The whole reason why we chose that point, and my suggestion at the very beginning, choose the y-intercept, because where does this line cross the y-axis? At this very point. In other words, that's my y-intercept, 1. So in this case, my b, or my y-intercept, equals positive 1. Now, had I chosen the other y-intercept, say I chose the y-intercept in this line, my y-intercept there would be negative 2, and so that would change a little bit of the format here. But again, just to describe what just happened, I found the slope of my line that I'm going to be measuring to, and I converted that to its perpendicular slope. Before, what I would have had to do is use my point slope form to find my y-intercept, but here's the convenient thing. Because I got to choose any point I wanted along that other line, the fact that I chose the y-intercept made that piece of work go away because that's actually the y-intercept itself. So my actual equation of the perpendicular line here, mx plus b, there's my m, negative 2x, and then plus b plus 1. There is the equation of my perpendicular line connecting that point to this line. All right, step 1, find the equation of the perpendicular line. Step 2, now that I have an equation that connects these two, let me scroll up a little bit here. So we just went through this process. This is that line graphed. There's my negative 2x plus 1, all right? There's that same y-intercept, and if I had done a negative 2 slope, I'd go down 2 over 1, down 2 over 1, and I create this line. This red line is perpendicular to both of my original lines. Okay. Now, this point right here is the kind of reducing this entire line right here down to its single point. This is the distance I'm going to try and find. Okay, but let's move on to step 2, which is finding the intersection. Because before I can do the distance formula, I need 2 points to find the distance between. And so far, I have this point, 0, 1, and I need to find the distance to wherever this intersects right here. But here is why going through the systems of equations problems examples I did in previous videos, this is where it's going to come in handy, because this will not be a friendly number. Even though it looks a little bit like 1, negative 1, it's not. And it's a little bit more difficult to see on my whiteboard without the coordinate grid, but if you were to do this on graph paper, it'd be a little bit more obvious. It's definitely not on something friendly. So here's where this is going to come in handy. We're going to create a system of equations. Well, the equation that we just found, this is the equation of this perpendicular red line right here. Y equals negative 2x plus 1. Now here, I'm going to scroll up for a second. Here's where crossing out this other equation comes in handy. Again, the reason we did this is because we chose that point. This point exists on this line, so I basically took this entire equation and reduced it down to 1 point. This is the other line right here that I'm going to measure against. This is the equation I'm going to use for this step 2. Had I done the other equation mistakenly, I would have found that the intersection would have been exactly there, and I'm just finding the distance between that point and itself. So basically, I would find a distance of 0. So it's important to do this process where I cross out the equation, I reduce down to a single point, and now I take the other equation to use here. So the 1/2 x minus 2 is going to be the other equation. And now I'm going to use my chapter 5 knowledge of finding the distance, or not finding the distance, forgive me, finding the intersection, the shared coordinate point between these two lines. So we're going to use the same process we did in the previous examples. Because both of these equal y, I can now set these pieces equal to each other. This is called substitution. So I would end up with negative 2x plus 1 equals 1/2 x minus 2. The two equations being set equal to each other. I have one equation now, one variable. I can get that variable by itself. I'm going to go through collecting like terms. I'm going to go through this a little bit quicker. I'm also going to convert this to a decimal because 1/2 conveniently comes out to 0.5. So if I add 2x to 0.5, I would get 2.5x. It's 2.5x, still minus 2, and then a positive 1's left over here. I would add 2 to both sides. I would get 3 is equal to 2.5x. Now I could divide by 2.5. Just to do this on a calculator, don't feel like you have to do this in your head. 3 divided by 2.5 is 1.2. So x equals 1.2. Not a friendly whole number, but again, using the system of equations, I get a very accurate answer. So it's 1 and just a little bit. That's the x coordinate point for that intersection. Now, how do I find the y counterpart? By plugging this value back into either of these equations. Just because it's nice whole numbers, let's plug it back into this one. So 1.2 times negative 2, and again, don't feel like you have to do it in your head. 1.2 times negative 2 gives me negative 2.4. Now I'd add 1, negative 1.4. So after plugging in 1.2 into this equation, it spits out negative 1.4. That's the y counterpart, or the y half of that coordinate. And now I have my coordinate point. So what just happened? By setting these equations equal to each other, this is just a little review of chapter 5 from first semester. By setting these equations equal to each other, what I'm essentially doing is I'm saying, where did this red line and this blue line share a coordinate point? And when I went through the process and solved for x, it told me the x half of that coordinate point, 1.2, 1 and just a little bit. Then by plugging that value back into the equation, it spits out what y equals, the y, the up and down half of that coordinate point, and it spat out negative 1.4, or down 1 and a little bit. So my coordinate point here is 1.2, negative 1.4. So now I can get into step 3. And step 3 involves my distance formula. And in order to use distance formula, I need 2 coordinate points. So all this work before was about establishing 2 coordinates to find the distance between. I started by picking one coordinate point right here. I took this entire line and reduced it down to a single coordinate point so I could find the distance between that guy and this guy. So 0, 1 is my first coordinate point. 0, 1 is this guy right here. Looks a little sloppy, but that's 0, 1. Now, my second coordinate point is this guy right here. Ultimately, all this work leads up to this part. I have now 2 coordinate points I can use for the distance formula. This one was found using my system of equations method to find that my second coordinate point is 1.2, negative 1.4. Now I have 2 coordinate points, and just to remind us where we would use this in distance formula, this would be x1, y1. This would be x2, y2. And my equation for distance formula is going to be the square root of x1 minus x2 squared plus y1 minus y2. squared. There's my distance formula. Those are the values I'm going to plug in. Just be careful of order of operations.